As we continue in chapter 10, we are going to go ahead and look at the properties of liquids. Okay, now liquids are important to understand. They're going to be a little bit different than the gases that we were looking for. And you can see some of the properties, the objectives that we have here. I do want to point out a couple of things that there is such a thing as viscosity. Now we think of water flowing easily, but liquids such as honey or syrup or even motor oil are going to have higher viscosities. They flow slower. So there's a property of liquids that is different and it's not due to the fact that it's a liquid. Okay. We also have attractive forces that are going to make droplets, like water forms spherical droplets. Okay. We also have such a thing as surface tension. So where like a mosquito can sit on top of water, water striders can walk on top of the water. There's a few other things that we see with surface tension as well. For example, the meniscus that we see in the lab. Now, on the right, you see a meniscus for water, and on the left, you see a meniscus for mercury. That's because of the different forces between the liquids and the glass walls. Okay. Notice we also have a capillary action. This water or wine in this case wicks up in there. They used wine so it could wick up in there. Actually, I think it's water with food coloring because um, I don't think they would use wine for that, but I could be wrong. Okay. Capillary tubes, the thinner the tube is, the farther the water is going to move up into the tube. And it has to do with the radius of that tube. Okay, so we've talked about a lot of different properties of liquids, but why do they exist? Well, it's because of the attractive forces. Now, in the case of water, water holds to itself very strongly and it holds to the walls of the burette. Those the adhesion forces. Those forces are both very strong. That's why we get the curved meniscus. Now, in the case of mercury, it isn't attracted to the walls of the glass at all, but very much to itself. That's why we have the opposite curvature on the meniscus of mercury. Now we want to look at phase transitions, and this is where we go from a solid to a liquid, or a liquid to a gas, or a gas to a solid, as I discovered when I tried to go out and leave this morning, and I could not see through my windshield because frost had formed on it. Okay, the frost didn't form from a liquid, it went straight from water vapor in the air to my windshield. Okay, so there are different phase transitions. Vaporization and condensation are between liquid and gas. Melting and freezing are between solid and liquid. Sublimation and deposition are between solid and gas. Okay. Now, vaporization is where a liquid is converted into a gas. And generally speaking, this transition occurs where we have some molecules going from liquid to vapor and some molecules going from a vapor to a liquid. This indicates something called a dynamic equilibrium. Okay. And the rate at which liquid vaporizes is equal to the rate at which the water condenses. This is an example. So if you have a water bottle with a lid on it, the water keeps evaporating, but it doesn't completely disappear because it's in a closed system. We have this dynamic equilibrium where water vapor also returns into the liquid. We can say the same thing with bromine. Okay. Once an equilibrium is reached, the number of molecules in the gas phase does not change, and we can measure that partial pressure. This is known as the vapor pressure. Okay. Here's a diagram of that exact process. So the vapor pressure is independent of the volume of the container, but it does depend on the intermolecular forces of the substance. Now, water has higher vapor pressure the higher temperature it goes. This is what you would expect. Okay, because at low temperature, a very small number of particles are going to have the kinetic energy to escape that surface tension, that intermolecular forces. As I increase the temperature, a greater and greater fraction of those molecules are going to have that. Now, if I increase the surface area, I have more of the molecules that are going towards the surface, so I will have faster evaporation as well. Okay, when the vapor pressure reaches atmospheric pressure, we say that's the boiling point. And we can actually use this Clausius-Clapeyron equation, the Clausius-Clapeyron equation, and we can relate vapor pressure to the pressures and the temperatures involved. You might see a problem with that. okay? Now, the last thing I want to talk about with evaporation is what happens if we go back and we take away all of the high energy particles. The average is going to decrease. So the temperature is going to go down. So when you sweat and that sweat evaporates, it actually does cool you down. Okay. Um, Remembering that we have transitions from solid to gas, the energy change required to go from a solid to a gas is the same as going from a solid to a liquid and a liquid to a gas. And we can call the sublimation, that enthalpy of sublimation. For the transition between solid and liquid, we have enthalpy of fusion. For liquid to gas is enthalpy of vaporization. And if we add heat at a constant amount, we can see a heating curve for water. Notice the very long, straight, constant temperature boiling until all the liquid finally boils. And phase diagrams. Phase diagrams are a result of the things that we have seen before, and they show us the different transitions. So for example, the vapor pressure, this is a vapor pressure curve right along in here. And I have a curve showing melting and freezing, and there's sublimation and deposition. Now, this particular substance is a normal substance. This is not water. I'll tell you why here in a minute. Okay. When we see water, this curve is actually a negative slope on the transition between solid and liquid. And this is why if you increase the pressure on ice, it will melt. This is not normal. Water is not normal. It behaves quite differently than everything else. Some other points of interest, there is a point at which all three phases of matter exist. This is called the triple point. The temperature at which above it you cannot exist as a liquid is the critical point. And we have a number of other bits of information. For example, here is standard pressure. So we have the normal melting point and the normal boiling point. This is a diagram for carbon dioxide. Notice the pressure is given into a logarithmic scale. But notice that we don't see the liquid at room temperature and pressure, okay? Even at 1 atmosphere, we don't see the liquid. That's way above here. Well, that's because carbon dioxide sublimes straight from a gas, from a solid to a gas at lower pressures. And we will finish out with the solid state of matter in the next video.